In this section, we're going to talk about arc length. What that means is the following. Suppose that you're given a function f of x in a closed interval ab, and we are assuming here that f of x is a beautiful continuous function. Let's say that now you consider the piece starting at x equals a and ending at x equals b. So I am only considering this piece of my graph. And let's say that I cut through, imagine that this was actually, imagine that the curve is made out of wire, and I cut through at x equals a and at x equals b, and then I stretch my curve and I put it against a meter stick. And in that way, I measure the length. So practically, intuitively, that's what we want to do. We want to be able to find the length of that entire curve from A to B. Now, in reality, given a function, I can assume that it's a piece of wire and that I can cut through and measure it against a meter stick. So what I'm going to do is I will divide that interval AB into many, many tiny subintervals. And then we're going to go ahead and consider tiny little segments that are going to join all of those little points. For example, I'm going to connect these two with a segment here, another segment, another one here, 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 and here. And you can imagine that the finer my partition is, the smaller those segments are going to be, so the more accurate the measure of the arc length of the curve is going to be in the interval AB. So in a while, we're going to be looking at what happens as the length of those partitions gets smaller and smaller and smaller, because we want to be able to get to the point of a very accurate approximation of the length of that curve. As always, A is associated with x sub 0. This will be x sub 1, x sub 2, dot, dot, dot. Let's imagine that there are many more subintervals after x sub 2. We're going to make this one right here the ith subinterval. So x sub I minus 1, x sub I, dot, dot, dot. We continue all the way until we get to B, and B will be x sub n. The same idea as with Riemann sums since chapter 5. By doing this, we are really saying that A, which is equal to x sub 0, is less than x sub 1, less than x sub 2, less dot, dot, dot than x sub I, and this is less dot, dot, dot than x sub n. And again, x sub n is B. So every x value keeps increasing throughout in the partition all the way up to B. This is not necessarily the same for the y values. If you notice over here, the y value at x sub 1 is bigger than the y value at x sub 2. And then things change. Then the y value here at this point is smaller than the y value at B, for instance. So with the y values, we cannot assume that this beautiful chain of inequalities holds throughout. Sometimes the y values fluctuate. The one that is after is bigger than the one that is before, or vice versa. Let's call the length of each of these segments L sub 1, L sub 2. So for example, this will be L sub 1, this will be L sub 2, and so forth. So then what we are going to notice here is that the length of the entire curve, I'm going to denote it by absolute value of L for length, that's going to be equal to the sum of the individual lengths, L sub 1 plus L sub 2 plus L sub 3 plus dot, 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 L sub I, the ith segment, plus dot, 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 L sub n. In other words, this is going to be equal to the sum as I goes from 1 all the way to n of the absolute value of L sub I. And this is a reasonable approximation for the length of the curve. Actually, in fact, I should have written the approximating sign instead of the equal sign. So let me go ahead and fix that. We should say that this is approximately equal to that particular sum. So much better. Now, what happens if I consider the limit all of a sudden? If I consider the limit as the length of the partitions go to 0. This reminds you of chapter 5 when we were talking about considering the limit. In other words, we consider tiny, like extremely refined partitions. If I consider the limit in this case as I goes from 1 to n, absolute value of L sub I, all of a sudden this becomes equal to the length of the curve. So what you notice is that the approximating side converted into an equality sign just by considering the limit as the width of those partitions go to 0. Now, this definition over here, it's good, it makes sense. Mathematically, it's a good definition for the arc length of a function in an interval AB. The only difficulty with this over here is that it is not practical. It's not going to help us in reality whenever we're given a function and we're asked for the arc length. For practical purposes, this is a little bit hopeless. What we need is something more algebraic, something that we can manipulate, something maybe involving the actual function f of x, derivatives. We need something algebraic. So this is what we're going to go ahead and focus our attention on. We're going to try now to develop an algebraic formula for finding the length of a curve in a closed interval AB. Again, remember the conditions that f of x, though, has to be continuous in AB. What we are going to do now is to focus our attention on the ith subinterval. We're going to keep this discussion general. We're not going to say the first subinterval, the second, the ith subinterval, so that everything is completely general. All right, so in the ith subinterval, x sub I minus 1, comma, x sub I, we will then generate these 2 points right here, the coordinates of this point and the coordinates of the other point. That means x sub I minus 1, f of x sub I, that's the point on the left, and then the other point is going to be x sub I, f of x sub I. And we're going to use that distance formula to find the length of the ith subinterval. So using the distance formula, that's going to give us a huge square root. This is going to be equal to x sub I minus x sub I minus 1 squared plus f of x sub I minus f of x sub I minus 1 squared. I'm going to go ahead and use as a simpler expression. Instead of saying x sub I minus x sub I minus 1, this will just be delta x sub I squared plus, we can do the same thing for the f of x, delta f of x sub I squared. So that becomes, so far, the length of the ith subinterval. Continuing here, we're going to go ahead and apply the mean value theorem. We know that by MVT, the mean value theorem, there exists a C sub I, a completely random C sub I, in the ith interval, x sub I minus 1, x sub I, such that the following is true. F prime of C sub I is equal to f of x sub I minus f of x sub I minus 1, all that divided by x sub I minus x sub I minus 1. So this is telling us pretty much that the numerator, delta f of x sub I, is equal to f prime of c sub I times delta x sub I, which is a fabulous result because now what we are going to do is we're going to do a substitution. We're going to take this expression on the left and substitute it within the radical. All right, so continuing with that substitution, we're going to have that the length of the ith subinterval will be equal to the square root of delta x sub I squared plus, and now on to the substitution. Instead of delta f of x sub I squared, we're going to write f prime of ci times delta x sub I. All of that squared. Factoring now delta x sub I squared, that will allow us to rewrite this as the quantity of 1 plus f prime of c sub I squared, brackets. And then, using properties of radicals, this will become 1 plus f prime of c sub I squared times the square root of delta x sub I squared. So what I'm doing here is a separation of radicals. So please note that this quantity inside of the radical here on the right, delta x sub I, is always positive. Remember that x sub 0 is less than x sub 1, x sub 1 is less than x sub 2, and so forth. So delta x sub I, that difference is always positive. That's a positive number. So then that means that when I eliminate the square root, when I write the square root of 1 plus f prime of c sub I squared, I don't have to write absolute value of delta x sub I. The absolute values are unnecessary. I can just write delta x sub I. So far, this is what I have for the length of the ith segment. What I have here is written down again the length of the ith subinterval that we just developed. And here I have the first definition for the arc length of the entire curve that we started with. The one that I was saying that is a fine definition, but it's not very practical because of the limit of the length of all of the sum of all that. So that's not very helpful here. What we are going to do now is to go back though to that definition and continue working this out by using now the expression that we just developed for the length of the ith subinterval. So then that means that the length of the curve will be equal to the limit as the width of the partitions go to 0 of the sum as I goes from 1 to n of the square root of 1 plus f prime of c sub I squared times delta x sub I. And I am hoping that you can now notice that this sum that we have over here is a Riemann sum. So now this can be rewritten as an integral. In other words, the arc length is equal to the integral from a to b of the square root of 1 plus f prime of x squared times dx. So again, as a Riemann sum, the idea is that the width of the partition is just going to 0. So this ci that we took in between, inside of the interval, ci nicely merges onto just x and delta xi becomes the differential dx. We have done this type of analysis, this type of argumentation many, many times when we talked about volumes of solids and so forth, when we were deriving those formulas for volume. Same idea here. So this is now the formula that we are going to use to calculate the arc length of a smooth curve in an interval AB. And if you notice, this is now very, very practical. Just simply an integral of within an interval of a function. And the function now is the square root of 1 plus the derivative of f squared. That's all that we have to use. This is now extremely practical. What I want though to point out again, in case you forgot, is that f prime of x is assumed here to be continuous. For this to make sense, we assume that f prime of x is continuous in the interval AB, because what we wanted was a very nice smooth curve. We don't want to have a curve with very large rates of change. We want to have something nice and smooth with no sharp corners or anything like that. Example 1 is asking us to find the length of the arc of the semi-cubical parabola y squared equals x to the third between the points 1, 1 and 4, 8. Semi-cubical, that shouldn't scare us. Imagine that I just come and I solve for y so that I express y in terms of x. This becomes y equals plus or minus x to the 3 over 2. And that already looks more familiar. Now, because this graph y is equal plus or minus x to the 3 over 2, I know that there should be another portion, another piece of the graph that goes down in that direction. Now, I don't really need to focus on this part that is below the x-axis, because I was specifically told that I need the length of the arc between 1, 1 and 4, 8. That takes me to the upper piece, the piece in the first quadrant. If this is 1, this is the initial point. This is now 4. This is exactly where we end. So I want the length of this arc right here. In order to do that, I will make use of the formula that we just developed. Notice that because I am dealing with the upper part, I'm going to be dealing only with the positive part of the function, positive x to the 3 over 2. And this function has a derivative that is definitely continuous in the closed interval 1, 4. That means that I can apply the previous formula. So the length of the arc, absolute value of L, that's going to be equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. We pretty much have everything in here. We know that a goes from 1 all the way to 4, the square root of 1 plus, and what I have to do right now is to work out the derivative. This is something that I can do here on the bottom on the left. F of x is equal to x to the 3 over 2. That really means that f prime of x is going to be equal to 3 over 2 x to the 1/2. So now I am going to take this expression and substitute it right here within the formula. That means that we're going to have 3 divided by 2 x to the 1/2 squared dx. Simplifying this a little bit more, that will give me the integral from 1 to 4 of the square root of 1 plus 9 divided by 4 x dx. So now I am faced with an integral that I need to evaluate. So now it just becomes a question about evaluating an integral. And I'm thinking here that perhaps we can do a u substitution. For example, I'm going to do this here on the right. We're going to let u equals 1 plus 9 divided by 4 x, that means that du will be 9 over 4 dx, meaning that we're going to have 4 over 9 du equals to dx. And now we're going to take this expression and substitute it here, and we're going to take our u and substitute it there. So continuing with the integral, we're going to have 4 over 9, the integral, and then the square root of u du. What I need to do right now is to adjust the limits of integration. Let's see, u is equal to 1 plus 9 over 4x. So when x is equal to 1, u is going to be 1 plus 9 over 4. That is going to give us 13 over 4. That means that here we are going to have in the bottom 13 over 4. And then for the other limit of integration, when x is equal to 4, u will be 1 plus 9 over 4 times 4. That will give us 1 plus 9, which is going to be equal to 10. So over here, we're going to go all the way to 10. So then that will be 4/9, the integral from 13 over 4 to 10 of u to the 1/2 du, and we are now ready to integrate. That's going to be here u 1/2 plus 1, that's going to be 3 over 2. And then we multiply by 2/3, and we evaluate from 13 over 4 all the way to 10. Continuing here, that will be equal to, now notice that I can multiply these coefficients to simplify my algebra. That's going to be 8 over 27, which will now give us 10 to the 3 over 2 minus 13 over 4 to the 3 over 2. So you notice that finding an arc length simplifies to making sure that the derivative in question is continuous in the given interval, and then just applying the formula directly. Then the next challenge will be the integral. Given that we have a square root, it doesn't mean that the integral will always be this simple to evaluate. Here, it boiled down to a simple u substitution, but you can imagine that very quickly an integral like this can get out of control. So sometimes the evaluation of the integral will be way more tedious than applying the formula. Sometimes the evaluation of the integral will be impossible to do algebraically, and the only way that you're going to be able to figure out an answer is to do perhaps a trapezoidal approximation. So you will be able to kind of approximate the integral and not be able to find an actual answer. So an approximation may be all that we can get. That will be exactly what's going to happen in the next example. In this example, they're asking us now to consider the hyperbola x times y equals to 1. Now you only see one branch of the hyperbola because I only drew the part that is relevant given the two conditions. They're telling us that we want the part of the hyperbola that is between 1, 1 and 2, 1/2. Namely, that means if this is 1, that takes us to this point on the graph. If this is 2, that will take us to this point. So we just want to find the length of this piece of the graph. Then, all right, in order to begin my algebra, I look at the equation xy equals 1, and then I solve for y so that things start making more sense. Y equals to 1 over x. The interval in question is the interval from 1 to 2. Then to start finding the arc length, well, I know that I will need a derivative. Let me do that right here at the moment. Y is equal to 1 over x. I'm going to write that as x to the negative 1. y prime is going to be equal to negative x, negative 2. That means negative 1 over x squared. And if you notice over here, that derivative is continuous in the interval from 1 to 2. So emphasizing that this derivative is continuous in the interval 1 to 2. That means that I'm ready to apply the arc length formula. So the arc length here is going to be equal to the integral from a to b, the square root of 1 plus y prime squared dx. That means that we're going to have the integral. Now, a is equal to 1, b is equal to 2. That will give us the square root of 1 plus negative 1 over x squared squared dx. Simplifying a little bit more, the integral from 1 to 2, the square root of 1 plus 1 over x to the fourth dx. We end up getting something like this. Now, you can try to think of a u substitution, you can try to get creative, and you're going to have a hard time evaluating this integral. This is exactly one of those cases where the best that we can do is an approximation. And I'm thinking here of a trapezoidal approximation. I also know that the approximation is more accurate whenever we consider a larger subinterval. In other words, a more refined subinterval. So I am not going to choose n equals 4, n equals 3. I'm going to choose more like a larger n. I'm thinking of perhaps n equals 10 to execute the trapezoidal approximation. Since this is the integral right here that I'm trying to approximate, that means that the function that I'm going to be dealing with right now will be f of x equals the square root of 1 plus 1 over x to the fourth. This is the function that's going to play a role in the trapezoidal approximation. I am going to use n equals 10. That really means that delta x is going to be equal to 2 minus 1, 1 divided by 10. I also have to calculate all of the x sub i's from x sub 0 all the way to x sub 10. You can see that right here, I calculated all of the x sub i's by using the width of every subinterval, which is an equal width of 1/10, starting with a, which is 1. So 1 plus 1 over 10, and then plus another 1 over 10, and so forth. And I end with b, which is x sub 10 equal to 2. So now, setting up the trapezoidal sum. So t sub n is going to be equal to 1/2 times 1 over 10, and then brackets. Then we're going to start with f of 1 plus 2 times f of 1.1 plus 2 times f of 1.2 plus 2 times f of 1.3 plus dot dot dot, and we continue in this way with 2 times f of 1.8, I'm going to skip a few in the middle, plus 2 times f of 1.9 plus f of 2. Now you take your time, you enter all this in your calculator, you add up all of these values, and you should have a pretty decent approximation. I use the calculator in order to help me out with the process. I want you to notice how here I created my table with the function, which is now the integrand. The function is the square root of 1 plus x to the negative fourth, as I mentioned a while ago here on the left. When I enter that function and I go to my table, then I entered all of the x values, all of the x sub i's in my partition. And the calculator immediately computes the y values. And these are the y values that I will plug in here, for instance. Let's say f of 1 is 1. F of 1.1 is approximately 0.909. F of 1.2 is 0.833. So when I carry on all of these addition and multiplication and so forth, if my calculations were correct, if I were careful inputting this into my graphing calculator, I am going to get that T sub 10 is approximately equal to 1.156. So then I conclude that the arc length, which is the integral from 1 to 2 of the square root of 1 plus 1 over x to the fourth dx, is approximately equal to 1.156.